Hey boys and girls, welcome back to Fastware. So I was doing my mandatory practicing at home and I found a problem which I wanted to share with you this time. So I found it on it a bit again. And this particular challenge is to given a location xy on rectilinear grid, you need to count number of ways to make it back to the origin point of 0, 0. So obviously, this is an interesting problem because there's just so many ways of solving this particular problem. But the notes strongly recommend to use some form of recursion. Now, I don't know about you, but I don't like these sort of suggestions because I kind of like to think through the problem myself. But what do you think? How would you solve this particular problem? So pause it, think about it, and let's continue with it. So when I read through the problem, I thought to myself, I think this might be a purely mathematical problem, not a computational one. And therefore I would be able to actually solve it by implementing a mathematical algorithm. So what I did is obviously do a little bit of research. So I found this paths on a grid problem, actually explanation how it's supposed to work. And I watched through, looked and tried to understand, solve the little problems that it gave me there. And I found that this is a problem part of the Pascal's triangles. And it's the n chooses k problem. So I did more research and tried to find as much information about these Pascal triangles, how they work, how they're formed, what individual parts mean, how the rows, how the indices in the rows are formed. And I found that there is a generic formula to actually do this. I thought, oh, cool. So it's a factorial function. I thought I could easily use that. So what I've started with is implementing this path by taking x and y. And it will take a form of x plus y factorial divided by x factorial times y factorial, which is pretty cool. So I implemented a factorial function. But for any of you diligent types out there, you will notice that I managed to fuck it up or screw it up. Sorry for my language. And I continue by implementing paths. So in a denominator, I have the x plus y. And then, in a numerator, I have x plus y. And then denominator, I have x factorial x times factorial y. And obviously the only thing is to divide one by the other. Right, so I think I needed to add a little bit of printing, but I decided to actually put it in the calling function instead. And just putting a little bit of information that I can keep track of what's happening before the function and after function. It helps me to understand calling and at which time things fail. So that's about it. And obviously, I immediately detect that the factorial function do not operate correctly. So I fix that and proceed. So here it is. Looks like I managed to solve all the problems apart from the last one, which is 1 times 99. So obviously I can see the problem here now. So 1 plus 99, it's 100 factorial. Yeah, that doesn't fit in anything. It's a huge function. It's a huge number that this function produces, sorry. So on a second day, I decided to do a little bit more research. I saw that the actually implementation that I was using was naive implementation or naive solution. And there is a better way of doing it. So I looked at how to do this, and there's even a small Java snippet there. And I took that and tried to implement it. So again, my path taken X and Y. And now this particular implementation relies that you can compute the nth row of the Pascal triangle, and then using an index into the data in that row. So the vector here will represent the row. Row data, each indexes will have values. So the first one will have 1, and then all the other ones are derived from there. So how that works is basically you have a previous value from the row data. So that will be from actually row data I minus 1. Then you need to compute a scalar, which is going to be the row minus I plus 1. The next is we scale the previous element by the scalar, so we multiply these together. And the last thing that we want to do is take a scaled form and divide it by the I, by that index. The property of this row data is that it's symmetrical. So basically it mirrors around the center, and therefore the beginning part of the vector and the end part of the vector will mirror each other, starting from the center. So I basically assert that this will be true, that row data at X and Y are exactly the same, and I just return one of them. Now, with my mandatory printing, I will try to test this particular implementation, as I think it looks pretty nice. It's obviously very different from what I've done before with the factorials. However, I ran into a problem again, where basically the row data X and Y assert that they are not the same. So I need to debug, find out what actually is happening and what am I doing wrong. I'm a visual creature, I like to see data right in front of me. So I just print this vector data onto the console, so I could actually examine it. So also I want some data about what I'm printing. So this is going to be the row, which is the X plus Y, and then X and Y individually, so I could determine what's actually happening here. Now, running this, I find that middle of this vector the numbers become huge. So obviously we're starting to overflow, therefore the end cannot be computed correctly, and we basically just pile up garbage. Next day, I think I can do better. So my understanding of that Pascal triangle, that it's mirrored around center, I say, okay, so what I can do is I take a minimum, so this column or the index into that row, minimum between X and Y. So therefore I only need to compute half of the row, not all of it. That's actually obviously helps. It's less steps and I can actually do something. Now I initialize row data to 36 elements. Can anybody tell me why I only need 36 elements? Pause it, think for a couple of minutes and let me know. Other than that, the algorithm inside of the loop to compute the row data is exactly the same. The only difference, as you probably notice, is that 128-bit type. So I use that for kind of a very weird reason. I want to check for overflows. So in 128-bit types, even if the previous time scalar overflows, I basically am able to infer that. So that's exactly what I do. I take from numeric limits the maximum for uint 64, as you can see happening on the screen right now, and I compare the scaled element with a maximum value, saying if the scaled element is larger than the maximum value, we have just overflown. Right, so now I just need to store the computed value and I can return the data. Hope this algorithm is simple enough so you can understand. There are some weirdness, I admit, but it should be pretty understandable. So again, my mandatory printing. Again, I cannot live without it. Can't live with it as well. So slow to do so, but I need to do it at least until I figure out what's what. And finally, I actually see some data. I can compute all possible results, and that's pretty good. Now I want to test the limits of my function. So I just dump a couple of limit functions that I wrote, trying to basically print the limit. So I can see that 12 and 166 in the rectangular thing, and 31 by 31 on the actually square grid. These are my limits. This is not limited by my implementation. It's limited by the uint64 maximum size, that maximum basically value that it can contain. Obviously, we can make it slower using a uint 128, but I don't want to do that. So what I do is just expand my test cases and obviously add a bit more tests for basically finding short paths, long paths, square paths. And I see how individual cases scale. But in release mode, compilers became so good so to hoist invariant reads and writes, so they basically optimize that code away. So I use quick bench. I see that that's happening exactly the same, and now I'm at CPP compiler explorer, and at 03 again I have no data. At 02 I have no data, and finally at 01 compiler does not hoist invariant reads and writes, and I can actually see some data. So locally I tried to do exactly the same thing, and voila, I finally see some numbers. So we have, so just want to put my machine to full performance mode, and I can see the finding path. So that's a mix, about 300 nanoseconds. Square paths are by far the slowest to do because they generate the most paths. But I think that's about it. I hope you learned something, how to solve these sort of problems. I hope you liked it. If you did, leave that like, subscribe if you haven't, and I'll see you soon. Cheers, bye!